Heyo, and welcome back. In today's video, we'll look at computer programming's first great leap forward from hand assembling code and writing it in binary to being able to write it in a symbolic assembly language. I'll cover a little bit of history, the design of a minimal SOAP assembler, and finally show off some of the assembler's operation and output so that we can see how we go about debugging assembly programs. But first, be sure to like, subscribe, and ring the bell so you never miss an episode as we take another dive into the deep end of computing with the EUP5108 microcontroller. In the very early days of computing, programs would be hand-assembled and written directly in binary, much like we had done in the previous video. What we want to do is write our programs in an assembly language such as this, and let the assembler keep track of the ROM and RAM addresses for us. Interestingly, even this first advancement faced pushback from none other than John von Neumann, one of the early computer science pioneers. When he first heard about assembly, he was unimpressed, and he was quoted as saying, "Why would you want more than machine language?" One of von Neumann's students had heard that he was using grad students to hand assemble his programs into binary, and this student took the time out to actually build an assembler. But when von Neumann found out about it, he was very angry, saying that it was a waste of a valuable scientific computing instrument to use it to do clerical work. But since I don't have access to a bunch of grad students to do the work for me, I'm going to go ahead and write my own SOAP assembler. In short, an assembler is a program that takes in an assembly language file and outputs the ROM file for you. The assembler keeps track of where you've put things in memory in both RAM and ROM, and so you don't have to constantly hand edit like we did before the actual address of every single instruction. The first simple assemblers would have been written by hand and assembled by hand to run on the machines that they were compiling for. But most modern embedded system processors have a set of host tools that run on the desktop, either Windows or Linux, and those tools were written in C. And that's what I did. I wrote my SOAP assembler in C to run on the Windows desktop, and I did the first part of that while on live stream, and if you'd like to, you can see that long-winded video up here. Or if you can't stand the long version, I also have a link to the shortened ASMR version that has just keyboard and mouse clicks. As it so happens, I was able to implement my SOAP assembler using just 11 command letters. So to give you an idea of how this assembler operates, it starts by parsing the file that's passed in character by character in order to retrieve a single line. Now, a line isn't the entire line. A line is defined as all the characters starting at the beginning of the line up until a carriage return or the hashtag character for comment. So these first 5 lines return empty. The 6th line returns initially all of these characters, but then we also strip off the trailing spaces. So each line, the line parsing logic, grabs just this part of the line. Then we look at the first character and see if it's in this list. So if it's a hashtag character, we've already taken care of that in the line parsing. In this case, we have a W character. The W is write the value of constant name. So write the value of main at this location in ROM, which since we haven't changed it, it starts at 0. And that's our reset vector. If you remember, the first 2 bytes are the location of where to start. So in this case, it's our main function. Then the next line, which would be O and this number, that is set the origin of the assembler's program address. And so in this case, we're setting it to 8 to get past the reset vectors. And then we're going to start putting in all our constant data, such as our strings. From there, we'll import all of the functions necessary to write both ROM strings and RAM strings, as well as read characters from the keyboard into a string in RAM. And so the whole point of this program is first to print hello world, and then print a prompt, and then get a string of characters into a buffer in RAM, and then print that string of characters. Initially, we have to set up that we want to start at main, then we want to jump past the vectors. Now we're going to start the next line with any content, which is ps string hw. And what that is the definition. So we create a constant name, in this case p string hw, and it is now equal to the value of the assembler's program address at this point, which we had just set to 8. So p string hw will be 8, and then we're going to start loading up some actual bytes. The next one in the list, the L, is what I would call hex literals. So it allows you to write values in 2-character hex abbreviations without the 0x in front of it. And what the assembler will do is take each one of those bytes and put them into ROM and incrementing the assembler's program address as it goes. Then we have S with hello world, and that does a similar function except it deals with strings. So this is my way of avoiding having to look up all of the characters or put some special escape character in front of every one. The S command writes character string into ROM, incrementing the assembler's program address as it goes up into the last character in the line. It does not include the trailing spaces, we've already gotten rid of those, and it does not include the null terminator. So in this case, right after our hello world, we want to do the literal OA, which is carriage return, and then the 00 to reserve a null terminator to our string. We do the same thing for the prompt. We define the prompt. Now, prompt is 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, so p prompt should be about 24. So we do the same thing for the prompt string. We define a label for this address location. We then say that our string is EUP in bracket. And in this case, we're going to print that prompt and then take characters in. So we don't want to put a carriage return. We just want to end it with a null. Then we want to define where our variables are in RAM. In this case, the variable to store our string. So we're going to start with A. That's a new command, so we'll show that. A sets the assembler's data address. So there's one number, the program address, which is continually incremented as you add things to ROM or define things for ROM. And then the data address is continually incremented every time you add things to RAM. But it doesn't know how much space to give it. So we had to create a separate command, the lowercase a, increases the assembler's program address by some amount to give you space for the variable. And there's capital V, which is similar to D, except that it defines a variable name based on the current assembler's data address rather than the program address. This is the next location of RAM versus the next location of ROM. So we say our character string is in RAM. We use the lowercase a command to add 20 to the assembler's data address, and that's effectively reserving space for 32 characters in the string. So now we actually start loading up code. We'll use the I command, and I is kind of like include in C. What it does is include the contents of the named file in at this point, and then after it's done processing that file, it continues. In this case, we're bringing in all of our EUP.io functionality, which includes things like getC, getAstring, and print from ROM and print from RAM functions. Then we define our main function, basically defining the label that we referred to initially way up here. So we define that label. Then we go ahead and print hello world by loading up the pointer to that string in the DR register, and then call print ROM. After that, we're going to create a label for the loop. So this is get a line and print it. We're going to load the pointer to the prompt, tell it to print the prompt. Then we're going to load the pointer to the string buffer in RAM, tell it to get the string or get a string. And then when we're done getting the string, we're going to write a carriage return. Then again, load up the location of the string that we stored in RAM, and then print from RAM, print carriage return, and then jump back up to loop. So as you can see, this is a much more straightforward way of writing a program, and the assembler will deal with all of the converting these mnemonics into their opcodes. let's go ahead and see how this assembles. We would basically just say EUP5108 and hello world.asm. There's our assembly. It assembled cleanly. The program size is 110 bytes. And if we take a look here, we can see how it interpreted each of the lines. And this is kind of equivalent to what would be referred to as a map file, where your source lines, line number and file name, are related back to the locations in ROM where things got located. So P string HW starts at 8, P prompt starts at 17 hex, which is 23, so I was close. And then you can see we got to line 27 of hello world ASM, and that was the include, at which point we start processing EUP5108.asm, and starting on line 7, we actually start having some code. Again, this is what would be referred to as a map file, and they're usually a separate map file for each source file, but I just included them here. And then down at the bottom, we have what's referred to as the symbol table. So these are the addresses in ROM for all of the constant strings throughout the program. And so here we go, main is 50. And then we have our variables in RAM, which is just the 1. And then some statistic information. It's 110 bytes, and we wrote out both a binary bin file and a ROM file that's easily loaded by Logism. So now that we have our program assembled, let's go ahead and bring up Logism and load that image. That would be hello world.rom. We've got the image loaded. Let's just go all the way to the desktop view and see how she runs. Reset, run. There's our hello world and yup prompt. Due to the speed of the simulation, it misses keyboard input sometime, like that space. So we type in a string and it prints out a string. Honestly, this is fun. There it goes. So I modeled these commands after other assemblers I've used in the past. So if you've seen the 6502 or Intel assemblers, then they'll look pretty similar. I think most of them have a dot format. So this would be .o for origin and the like. In any case, the idea is much the same. So you might ask what the O, or optimal, in SOAP means. Well, what it amounts to is that when you are writing a program like this and hand assembling it, as a way of convenience, or as a matter of convenience, I would put things like each individual string would be on an even address, right? So 100, 170, 250, and at the same time, I would put the code in a fixed location that was convenient for my memory of what each function address was. What that leads to is a gappy kind of ROM where there's lots of empty space in between things. Whereas in the new assembled version, if we look at all the zeros, they're pretty much only after it. And so the assembler, knowing where everything was going to be and keeping track of all the addresses, and it's able to be a little more compact in its assembly. Now, we may want to do that, we may not. In a lot of cases they don't. Often they start off, the embedded targets I've dealt with will start their programming at 400 hex or 4000 hex or something to that effect. And that's the function of the O command in our assembler. So let's take a look back at our source code. If we wanted to, we could use this O command to set the start of programming at 100 hex. Then if we do our assembly once more and take a look at our program ROM. Oh, something went wrong. Oh, yeah, this happens a lot. I didn't save the file. Save the file. Rebuild. And you can already see the addresses have changed here. P string and P prompt, and then we jumped off to 100. And it thinks that our program is now 338 bytes. is really just printing the last assembler's program address at the end of all of the assembly. But if we go ahead and take a look at the ROM file, you now see we have a big batch of zeros between our strings and our program space. And you might want to do that just so that you have space for these without having to relocate those. But again, the assembler handles all the numbers for us. Also, the assembler helps when you do things like accidentally mistype a name, or in this case, since my assembler is case sensitive, if we change the name here and try to assemble the program, we actually get an error during processing. And that is that we have an undefined symbol, main hello world ASM, main being the symbol. And if we look through the printout, we can see we did define main. It's actually defined here. It should be 134, but it's lowercase. So we could actually change it one way or the other. But let's go ahead and just change this from main, this one to main, capital M, main. Go and build, and there you go. Everything builds cleanly. Now you may have noticed that I only gave myself space for 32 characters on the input string. So let's see what happens when we go too far. Let's do start at 1. That's 10 characters. 20 characters. There's 30, 31, 32. Now let's see what happens. Didn't print it. So where are we? Well, it looks like we've gone off into the weeds, writing code to I don't know where. I think what happened is we actually ran out of RAM and we overwrote our stack return address. So when we returned, we actually went off into oblivion somewhere. Actually, what we want to do is if we ever get off into the weeds like that, we want to stop. So rather than filling the ROM with 00, which is the no op instruction, let's fill it with a 11, which is the halt instruction. So conveniently, I've added that feature to the assembler where I can say 0x11, we assemble, take a look back at our ROM, and sure enough, everywhere where there were spare zeros, it's now 11s. So if we ever get off into the weeds, we're going to halt and we'll be able to look at what's happening. We have to go back down to here to reload it. Reset. Hello world. All right. Let's type in 32 characters. And there you see, the last two characters we were 0 and 1. So if we press enter now, sure enough, we went off to a location that was 3-1, the last character typed, and 0-0, which was the null character from pressing enter. And then we returned to that location and increased it by 3. That's part of the way you return from a function call, is to get past the original instruction call. Better than running off into the weeds, allows us to debug what's happening. Clearly we shouldn't have our address so high up in memory that we're colliding with the stack. This is something most people don't have to worry about in modern systems as they separate the stack from the heap and provide memory guards around it using the hardware of the memory controller in the modern processors. So this was great for debug, but what if we had this device fielded and somebody typed in the wrong number that led us off into the weeds? We wouldn't want to halt, we'd want to restart. And we can actually do that in our assembler, because instead of 11, we can use the AA instruction, which is the reboot instruction. Let's take a look back at the ROM. AAs. Let's try it again from here. Reset. 10, 20. Sure enough, we went off into the weeds. It was a place we weren't expecting, so we just rebooted. So if you'd like to follow along with what we've been doing here, we have all the files for the virtual microcontroller up on our Patreon to anyone at any level. And if you can't support us through that, please consider supporting us on one of our crypto tip-in links. We're hoping to get monetized soon, but it's a long road to monetization. And that's about all I had for this one. Please join us again next time as we get from the deep end, maybe up a little bit closer to the shallow end of computer programming, now that we can actually write in assembly language. We'll see you next time. Hey-o, how's this? Hey-o, and welcome back. Jesus, Google. Today's video is in binary over to a symbolic assembly language.